Hi, in the part one of the video, we looked into what is caching, how caches, and the internals of the cache, and how caches are used to improve the performance. If you are coming to the part two of the video, I would strongly recommend to go and look into the part one of the video where the fundamentals are discussed. Now, let us look into some of the caching strategies. The first strategy we are going to look into is the cache assay pattern. So, what's a cache assay pattern? The reads, whenever somebody tries to read the data, the reads are served from the cache if the data is present in the cache. Okay. But if it is not present in the cache, the underlying data is served from the DB and then put back to the cache, and then the data is served. This is how the read flow works. Read from the cache, if present, return. If the data is not present in the cache, read from the database, push it back to the cache and serve the data. Write flow. How does the write flow happens? Whenever a mutation or a new insert of the record comes, let's discuss about the mutation. You write to the DB and then give it back in terms of new insertion. The data is not updated into the cache immediately. That's one thing. If the data is already present in the cache and somebody is trying to modify the data, go and write it back to the DB, but invalidate the cache. Why are we invalidating the cache? We'll look into that in the upcoming slide or in a later point of time, but that's what it happens in the cache aside pattern. This is the read flow, which is explained in a small flow chart. Read request comes. If the data is present in the cache, return it back. If it is not present, read from the DB, put it back to the cache, and then serve it back. Okay. Write flow, write to the cache, write to the database, invalidate the cache on mutation. If the data is not present in the cache, no problem, return it back. It means that the new insert has come in. Okay. So when the cache will be hit and when there will be a cache miss in terms of the cache assay pattern. When the data is present in the cache, it means the cache is hit. Otherwise, the cache is not hit. When the cache miss will happen, this data is newly inserted. I'm not able to find in the cache. So obviously, I'll have to find it from the underlying data sink or the data layer. And if the data is mutated also, previously it was present in the cache, now it will not be present in the cache. Third scenario, when the cache is expired, usually caches expire after a TTL, because what happens is if if we don't expire the cache data will keep growing, and one day the cache data will be equal to the amount of data which is in the database. We already looked into the part one of the video that caches store only a part of the data, not the complete database is not put in the cache, because not the complete database is not accessed very frequently, right? Only frequently accessed items are put in the cache. Okay. We will look into TTL in a separate video. Caches and TTL is a complex problem to be solved. How do we manage TTL in a cache itself is a very complex problem. Let's look into in a different video. But when the caches expire, the caches expire based on TTL, as and when the cache gets expired, we will not be able to find the item in the cache. It is comes a cache scenario. Let's understand that and then move forward. So what are the things that we need to understand? The data is lazily loaded in this pattern. It means that the data is not eagerly loaded. Why? What is eager loading? When the data is returned back to the cache and then immediately it gets pushed into the cache also. The data is become to the DB and then it pushed to the cache. It is called eager loading. Lazy loading is when the request comes to access, then I will try to load. That's called lazy loading. And all mutations and TTL invalidates the data. What is the drawback? Does this Is this pattern suitable for all the scenarios? No. What happens there is when on a spike load, an item which got inserted and everybody is trying to view the data, what happens during that initial period of time, the spike cannot be avoided because the data, newly inserted data, immediately doesn't come to the cache. The data is inserted and everybody is trying to read the data on a per second 1000 requests comes. Till the first request is served from the cache, all the 999 requests will also try to get loaded from the DB. That is something which we need to understand. Okay, before going through the next caching pattern, which is the write through cache, we will discuss the pros and cons. Why? And also look into why the write or the mutation invalidates the cache. We spoke about that in the first slide. When we write, we invalidate the cache. Why do we need to do that? The underlying purpose of cache is to get the data loaded, served faster. Why are we going and invalidating a cache? And we also discussed that caches are the scenarios where the data could be eventually consistent. Maybe the user is okay to view the older version of the data, but why this process eagerly goes and invalidates it? That's an important question that we need to understand as part of the cache assay pattern. Usually, we are intuitively programmed to think like that. What happens is the caches doesn't mean it's a atomic data. Sometimes a complex data could also be stored, like user persona, like phone number, address, and other recently added items. All these things can be stored in the cache for a particular user ID. What happens when a subset of data only is mutated, right? We will have to go and look into all the other places, join together, and put it back to the cache. That might slow down the write time. So this could be one of the reason where the data mutation, any mutation on the underlying data, we will invalidate the cache because it itself is a lazy load pattern. We will do it back. Can't this be solved in a different way? Yes, this problem can be solved using a pattern called change data capture. Whenever the underlying data gets modified, we can put it back to the cache by using change data capture. But we will look into that later. One of the scenarios why the data is mutated or mutated data is being thrown away is that the underlying data can be complex. Maybe it is stored in scattered across multiple tables. Refreshing the data or putting it back takes time or slows down the write operation. That is why we are not doing it. We are just clearing it off, which is again a constant operation that we need to keep in mind on the cache asset pattern. Okay, let's look into the next pattern, which is called write through caching. Caches are refreshed as the data is written to the DB layer. If it is done atomically, as the read will always see the updated data. An important point. When a write happens, immediately the write ensures the data is also pushed back to the cache. If the write back to the cache happens little later or eventually, sometime there are chances that people will see the old version of data. It is the responsibility of the write system to ensure the cache is updated post writing to the underlying DB sync or the data storage area. This is called write through caching. Read flow, since the write system ensures that the data is written back to the cache, all the reads are directed only to the cache. Literally, if the data is most cases, the data is served from the cache only. Okay. So this is the diagram. Read from the cache, return. Write to the DB and write to the cache. Okay, that is the way that we do. When cache will be hit? When the data is present in the cache, the cache is hit. We will not try to load because it is ensure that any new data, any mutation which puts the data back. Whenever the data gets mutated, it means that that data is going to get accessed. I will read it file. Usually, the underlying data or the data sync is not been the data storage layer is not been probed through to get the cache, but it could also happen. When there will be a cache miss, the data is not written back to the cache, then there will be a cache miss. For example, a write succeeds in the database and the write is not able to put the data into the cache, then it is a cache miss scenario. When the TTL is expired. Okay. When the TTL expired, obviously data. Here the data is eagerly loaded into the cache, which means that every write loads the data into the cache. All the mutations also refreshes it. Whenever the mutation happens, even when the underlying data is a complex thing, it is the responsibility of the write system or the mutating system to put the data back to the cache. So as we discussed, what is the drawback? If the underlying data is spread across different entities, updates becomes complex. Since if this can be solved in a different way, as we talked about change data captures, but what happens is, and the system can be eventually consistent. This would not be a problem. But if this system has to be immediately consistent, it becomes a trouble. Uh, for example, if we have to be immediately consistent and the data is served from the cache, it becomes difficult. But this problem can be solved using some of the distributed design system patterns like transactional outbox. I have a separate video to explain about how transactional outbox problem solves uh, atomically writing to two different storage layers. So you can go and look into it. I'll paste the description of that video in this video link so that you can go and refer what is transactional outbox pattern. There are chances that the data can be stale. Okay, before looking into the refresh ahead pattern, which is the next caching strategy that we are going to look into it, we'll dwell a little deeper into what are the things that we can do to ensure that the data is put back to the cache. We have discussed in the past two caching strategies, cache aside and the write through. There is some concept called CDs. What is change data capture? This, if we go into the depth of CDC, we can put a separate video on that, but I'll give you an overview of what is CDC. Whenever an underlying data gets changed, right, the underlying storage engines will raise an event saying that the data is changed. Many systems listen to it. For example, uh, Cassandra, some of the relational databases emit that this data is changed. Couchbase emits CDC. So this change data capture, usually the data is replicated, right? We talk about data replication as a strategy to ensure the data is highly available as well as the read can be done. Data is replicated using CDC systems, using a manner called change data capture. Whenever a change happens, the data gets replicated. So we can listen into this change data stream and then get the data back. Many databases offers this, but what happens is we have to, the reading system who is listening to the change data capture has to ensure that the data is processed in a guaranteed manner, underlying guaranteed manner. The underlying system emits only one event. It's like fire and forget. The event gets emitted. It is the responsibility or the onus of the application processor to actually listen or process the changed event in a guaranteed manner, which itself is a complex problem, but this is called change data capture. Anybody who is studying distributed systems should be aware of this change data, and the guarantees of change data capture is not the responsibility of the person who is emitting this event, but it is the responsibility of the processing person or the processing system to ensure guarantee. We use that and then guaranteedly write it back to the cache. This is a way, not the way, to ensure the cache is written back as well without putting much load on the DB. Okay, or without putting much load on the application layer also. If we, I said about the transactional outbox pattern, it is the onus of the application, right, to write it by using a bigger transaction. We need not do that because these are two disparate systems, two systems which are running in different process boundaries. So this change data capture is one of the easiest ways to process it. We looked into two caching strategies. Let's equate to the other strategy in the next video or part 3 of this video.